The electrical grid operates under a strict physical constraint. Every single watt of power must be generated the exact millisecond it is consumed. When you flip a switch, a power plant somewhere must instantaneously produce that extra energy. This graph shows the grid's heartbeat, which engineers measure as frequency. In North America, the system is designed to operate at exactly 60 Hz. That precise line tells operators that supply perfectly matches demand. If demand suddenly spikes and outpaces supply, frequency drops. A significant drop forces heavy equipment to disconnect, which can trigger widespread cascading blackouts in seconds. Right now, we are retiring traditional power plants and replacing them with decentralized rooftop solar panels. While deploying solar reduces carbon emissions, it inadvertently removes an invisible physical property that has protected our power lines from collapsing for over a century. To keep the lights on through the green transition, engineers have to find a way to replace a property we rarely ever had to think about: grid inertia. For 100 years, our power relied on enormous, heavy machines. Conventional coal, gas, and hydroelectric plants use a piece of equipment called a synchronous generator. They force high-pressure steam or rushing water over giant steel turbines, physically spinning massive shafts to produce alternating current. This diagram shows how synchronous generators are linked by electromagnetic forces, spinning in perfect lockstep. If one fails, the shared momentum of the remaining turbines resists slowing down, acting as a physical shock absorber to buy the grid crucial seconds. Grid operators didn't have to program the safety feature. It was a natural byproduct of using heavy, rotating steel to generate electricity. Solar panels don't spin like traditional turbines. They are completely static devices with zero moving parts, silently converting sunlight. Because solar cells generate direct current, or DC power, they require an electronic device called an inverter to convert that power into the alternating current the grid uses. This chart shows daily electricity demand, and you can see a deep valley forming right in the middle of the day. That drop happens because millions of homes generate their own solar power at noon. To prevent the system from overloading, operators are forced to turn off heavy traditional turbines. Without those heavy turbines spinning, the grid becomes physically lighter. If a cloud bank blocks the sun or a transmission line fails, there is no spinning mass to absorb the shock. Frequency drops incredibly fast. Deploying static, clean energy has inadvertently stripped away the inherent kinetic stability that kept the grid upright. Critics often argue that because renewables lack physical mass, a stable power grid will always require burning fossil fuels to provide a reliable baseline. But grid stability doesn't actually require thousands of tons of steel. It strictly requires rapid, perfectly timed adjustments to supply and demand. Engineers are rolling out a new class of technology called grid-forming inverters. Instead of relying on mechanical momentum, they use software to emulate it. This microprocessor actively monitors the grid's voltage and frequency. When it detects an imbalance, it instantly injects power to push back against the disruption, creating synthetic inertia. Connected to battery systems, it corrects grid failures in milliseconds, far faster than a heavy steel turbine. We are replacing a mechanical safety net dictated by mass with a precise, high-speed digital response. The old model of relying on a few massive, centralized power plants running constantly to provide baseload power is becoming obsolete. We're moving toward a distributed, active ecosystem. Millions of smart inverters and home batteries constantly coordinate and adjust instantaneously, keeping the system perfectly balanced. Transitioning to clean energy requires us to completely upgrade the electrical grid, turning it from a rigid, heavy machine into an agile, highly intelligent digital network.